Hello everybody, welcome to part 2 of your unit review. We are moving on to question number 5, which says, suppose that Monique has $4,300 to invest. She deposits the money into an account that pays 6.8% interest compounded continuously over t years. So in letter A, it asks us to write a function a of t to represent the balance in the account over time. So make sure that you're using the variables that you've been asked to use. So a of t is going to equal, this is an exponential growth problem, and we know that it's being compounded continuously. So if you remember from your formula, that's going to be y is equal to your principal times e to the rt, or pert, as some people like to call it. So in this case, our y value is just going to be our function a of t. The principal in this case is the $4,300 that she has to invest. Since it's compounded continuously, my base is e, and I'm going to raise it to the rt. In this case, my rate is 6.8%, or 0.068. So 0.068 t. So there's my function a of t that gives us the balance in our account over time. In letter B, it says to write an equation to represent the inverse. Okay, and so again, in this time, we're going to switch our variables. Now, we're not using x and y in the original equation, we're using a and t, but if you're more comfortable using x and y, I would recommend doing that and working through the problem and then putting it back in function notation when you're done. So if I switch my variables, that means that this is going to be x equals 4,300 e to the 0.068 y. And the goal, of course, is to get y by itself. And so what I'm going to first do is I'm just going to circle the quantity or put a square around the quantity that I need to isolate first. I want to isolate the quantity that involves y, and that is going to include the base e, but not the 4,300, which essentially, to get rid of it, since I'm dealing with multiplication, I'm going to want to divide both sides by 4,300. And so that leaves me with x over 4,300. And that now equals e to the 0.068 y. Now, to get the y out of the exponent, I have to rewrite this equation using what I know about the inverse of an exponential. And the inverse then is going to be the logarithm. So think about your base. When you write a logarithm, your base is going to stay the same. So I would start off writing log with base e. And then I want to think about my other quantities. When I write the inverse, remember I'm switching the quantities. So my base e, I'm going to have the log of x over 4,300, and that is going to equal 0.068 y. And then my last step is now just to get y by itself, which I can do with division. And so my final answer then would be that y is equal to, now the log base e, remember, is just the natural log, and that's how you have to be able to recognize it on the test. If you wrote log base e, that's not wrong, but just know that on the test, or what you'll see in a book, is going to be the natural log, which is ln, and then the denominator is going to be 0.068. Now, this function, we didn't call it y to start with, we called it a of t. So you can put an inverse notation there, but we really want to refer to this function as a inverse of t. And since I started off using t, I really should be using my t variable in the equation. And that way I'm back to the original variables in the function, a and t. All right. Problem number 6. This is a problem that's very similar to the one we did in class, where, in fact, it's the same problem. I just used different numbers. A biologist is examining the growth of a dangerous strain of bacteria. You're given the data from the experiment. Remember, when you're given data, that's basically called statistics, and we want to go ahead and enter our statistics into our lists. There we go. All right, so we've got 4, 6, 9, 12, and 14. And then in my second list, I want to make sure that I'm typing in these values exactly as they appear. It's in scientific notation, but I can type this in as 7 times 10 to the 7th. And then I'll have 7 times 10 to the 9th. 7 times 10 to the 12th. 7 times 10 to the 15th. There's another way that you can enter scientific notation into your calculator, and it actually uses the E. Notice that above the comma, there's a double E. That's another way that you can type in scientific notation. So for example, this last data piece is 7 times 10 to the 17th. What it's ultimately going to say in my list is 7E17. Well, I can just type in 7E17. If I hit 7 and then use my blue second button and then hit my comma key, that's going to give me the EE button. And now I can type in 17. And that's another way to enter in function notation, scientific notation. Sorry, I've been talking too much today. All right, so now that my data's in, it says in part A, the biologist expects the growth of the bacteria to follow an exponential pattern, determine an exponential equation to model the data. When you're talking about modeling, you can certainly try to do like a sequence, but I think it's easier since we've just entered the data into the calculator to let the calculator come up with an equation of best fit. And so that means that we're going to go and do exponential regression. So if we go to Stat and then go over to our Calc menu, we're going to scroll down until you see the option that allows us to do exponential regression. Oops, I went too far. Okay. All right, you do want to make sure that your X's and Y's are coming from the appropriate lists, and you also want to make sure that you store your regression equation in Y equals. So I'm going to go to vars, Y vars, and I'm going to use function Y1. And I'm going to press enter until it gives me my equation. All right, so our equation for our bacteria, I'm going to use B of t because that's the name of the function that I'm told to use. My value of A is 7,000. That's how much we started with. And it looks like it's growing at a rate of multiplying by 10 every day, apparently. Okay, and I'm going to use a t as my exponent because that's what the equation tells me to use. All right, so there's my model. Part B says that the biologist thinks that if the bacteria continue to grow to be more than, so the B of t, remember, is the number of bacteria. And if the number of bacteria is more than 7 times 10 to the 28, now remember in your list it's going to look like 7E28. If it grows to be more than that number, then it'll kill the host. So according to the model, how long will that take? You could certainly use your graph here, and that's usually what I would recommend that you do. But for this problem, it actually works out a little bit easier if you use your table. So if you hit the second and go to your table button or your table menu, sorry, my computer's not calibrated. Okay, so if I go into my table now, I can see that all my X's, I can see all my Y values. Now Y2, I have another equation in there. We can ignore that for right now. In fact, let me go ahead and delete that second equation because that's something that is old. Okay, so now when I look at my table, I'm looking for the Y value of 7E28. Well, look where my X's are right now. I mean, I can keep scrolling, but it looks like I'm going to have to scroll. Well, I'll just keep scrolling. It's not too far. I went too far. Sorry. My calculator has a little bit of a delay. And it'll keep going. All right, so I want to make it so I see 7E28. There we go. All right, so it takes 25 days for the bacteria to reach that value, which is going to be 7 times 10 to the 28th power, which is quite a big number. That's why you can't see all the digits in the calculator. It'll just round it to 7 times 10 to the 28th. So it's 25 days. It'll take 25 days to kill the host. Okay. In part C, though, it says that a second model is developed by the lab assistant. And I know that this model looks really scary, but it's actually quadratic. It's something times x squared plus something x plus something, which is just a quadratic equation. I'm going to enter this in another y equals equation, so in y2, and again, I'm going to type it just the way it appears, 1.6, and you can either use your e or your times 10 to the 16th, whichever is easier for you. I'll go ahead and do it times 10 to the 16th. Do be careful on the new calculators though, because they'll actually push the cursor into your exponent. You do need to pull it back down before you keep typing. And then I need to type in my x squared. And then I've got plus, and then I'm going to have a negative. Make sure you're using the negative button and not the minus. 10, and this time 10 is to the 17th power. And again, I'm going to move my cursor out of the exponent, type in my x, and then do plus, and then 7.7 times 10 to the 17th. These are some big numbers. Okay. And so essentially what I want to do is see if that model gives me the same results, if it'll show that the host can live for 25 days. So I'm going to go to my table again. And notice here, when I scroll down to 25 days, I know that with the model that the biologist had, the number of bacteria was large enough that it would kill the host. It was 7 times 10 to the 28th. But if I look at the other model, it's 4.8 times 10 to the 18th. That's a much smaller number. So the host is still alive on the 25th day. And if I keep scrolling down, I can see that it takes quite some time for that number to increase. And so, I mean, now we're at 45 days, and I'm still looking at times 10 to the 19th power. So according to the lab assistance model, the host can continue to live well beyond 25 days, and that's what I'd want to put. Okay. If you wanted to keep going, you certainly could. If you wanted to increase, like if you go to your table set, you can increase the increments of your table. Like if I increase them to 1,000, I wonder if that'll make a big enough difference for me to be able to see. Yeah, I mean, even if I increase it by 1,000, it's still taking quite some time for me to see times 10 to the 28th. I mean, I can keep going, but I think you can see that we're talking about 48,000 days. We're well beyond the 25 days that it took for the original model to kill the host. So the two models don't agree. All right. Number 7, this problem you're not going to be assessed as part of your unit test, but I am going to assess you using the rubric that we used a couple weeks ago when it came to argumentative writing. So this time, though, I've also given you a graphic organizer to help you organize the information that you should include in your write-up. I'm not going to do this problem with you because I do want to assess how well you can construct your argument, but I do want to help you kind of organize your thoughts. You're given some data. It says a savings account contains $1,000, which earns 5% annual interest compounded continuously. The number of years, which we'll call Y, the money must be left in the account for it to grow to a balance of X dollars as given in the table. Which type of function would be more appropriate to model the data? Would it be exponential or would it be logarithmic? Notice that if you're going to do exponential,